Alrighty then, let's get going. So I'll start with a quick PSA and remind everyone who is on right now to quickly confirm that you are muted, please, as we go through the presentation. That'd be lovely. And we on the IES board would like to welcome everyone and thank you all for joining us today for this review of the NEC Article 700.2 Emergency Lighting Control. Very riveting stuff, as always. My name is Carl Canfield. I am the education chair on the board and also just help with general programming. And I'm a project manager over at GLS, Lighting and Controls. I am introducing our presenter today, Mr. Shane Lacey, who you may or may not be familiar with. Shane moved to Colorado in 1998 to start local business here, and that business transitioned into GLS, George Lacey Sales, in 2003, and took on the form, generally the form as we recognize it today. Shane has been the trusted advisor to the local lighting community ever since. Over the course of Shane's career, he has blown up at least one of everything he's touched. He spent about 25 years as a production DJ doing sound, visual, lights, and has done production work for such august artists as Marky Mark and the Funky Bunch. So if you ever get the chance to ask Shane about that, please do. He'd love to share the stories. So with that, let's get going. I'll hand it over to Mr. Shane Lacey, and have fun, everybody.
Well, thank you, Carl. I'm not sure I can top that introduction in my presentation. Interesting times. I'll have to go back home tonight, get that box of tour t-shirts out, pull the mothballs out, and see if I can still fit into those. Thank you, everyone, for joining us for emergency lighting control discussion today. Our subject matter will be the updates that we've seen in 2020 to NEC Article 700.2, where we have some definitions, and specifically Article 700.24, 25, and 26, and their associated updates in 2020. These particular codes update every 3 years, so we've seen updates in 2011, 2014, 2017, and now 2020. So it's fairly easy to understand why a specifier might be slightly confused as to the current state of the code, and or there might be a condition where their design standards have fallen a bit out of date. So hopefully today, by going through these standards and some specific how-tos and hardware pieces, we will help everyone understand where we're at in these codes a bit more. So one might ask, why is this code changing so much? And the basic answer is the lighting control industry changes. So not only have we had advancements in lighting control technology, but also in their requirements, particularly in aesthetic design requirements, where an architect would prefer to use the egress and the normal lightings for regular lighting, as well as using the egress fixtures for egress lighting, so they don't have an alternate set of egress lighting fixtures, such as perhaps battery powered frog eyes or a dedicated set of fixtures that are only used for egress. Distributed lighting control networks compiled with lighting energy management have resulted in much more discrete and refined lighting zones. So things like daylight harvesting, integration of occupancy zones have resulted in much smaller lighting control zones. So the Code Review Committee has to address those standards. Integration of LED lighting into our industry has resulted in more control techniques for lighting fixtures. And the real crux of the changes is a demand for and a requirement for predictable performance in the event of a power outage. So our learning objectives today, we'll start with define or understanding the definition changes that we saw in Article 700.2 in 2020, and then the changes to 700.24, which is where we see the description for an operational intent for controllable luminaires. Article 700.25, BCELTS, branch circuit emergency lighting transfer switch, and 700.26, ALCR, or automatic load control relay. And while these particular code sections describe performance and operational criteria, a higher level intent is often lost in a bare bones interpretation of these specific articles of the code. Specifically, the assumed fiduciary responsibility of the specifying engineer or designer of a life safety rated system is sometimes gets lost in the minutia of getting the job out the door. So we may not have discrete evaluation of the application for this particular job. And this habit is easy to repeat, as there's never an issue until there is an issue. So previous designs get repeated, previous boilerplates get repeated, and the code review committee issues use guides and bulletins between these code updates to specifically assist in reducing misapplication of code intent. So content use guidelines and bulletins are often the basis of code changes in the next code cycle. My next three learning objectives are elements that do get overlooked in the minutia of getting the job out the door. So first of all, the fiduciary obligation to develop a specification that results in predictable performance in a power loss condition. Predictable performance is underlined because we're going to hear about that throughout this presentation. So when we're dealing with a life safety issue, we definitely want predictable performance. In order to get predictable performance, we may have to do additional deep dive understanding of the products involved. We may also need to look at the situation and say, hey, I may or may not have control of the light fixtures supplied in this situation. How can I develop my specification to ensure that regardless of how the light fixture is controlled, the device used to control that emergency luminaire is compliant and the operation of it is predictable. Right along in that groove, recognizing that a product that's UL listed doesn't mean that it's the proper application of the listed product in that application. So let's remember that these are life safety systems, and designers should try to move away from decisions based on economics or commercial packaging concerns so that the methods applied are proven and robust and result in predictable behavior. So a few clarifications before we deep dive into this. We often see on a set of drawings a box and a reference, maybe a UL 924 device for control of egress lighting fixtures. So UL 924 is a UL evaluation criteria. It's not a qualified specification of a product. There isn't a UL 924 product. There are certainly devices that shall be evaluated to and compliant with UL 924, where UL 924 is the evaluation criteria that the product may have to go through. So where do we see UL 924 used as a common evaluation for lighting control devices that would fail on upon normal power loss? So obviously exit signs or perhaps emergency luminaires with internal batteries. UL 924 code applies to these devices. An ALCR or automatic load control relay, and that's highlighted because we will talk about that product today. Directly controlled luminaires and their associated bypass equipment. We will also talk about those devices today too. Dimmer relay systems that are used under Article 700.23 would also be evaluated with to a UL 924 standard. The items that aren't highlighted, we will not talk about today. We're speaking specifically about zone level control devices today. Another clarification in regard to the UL 1008 UL standard. That again is an evaluation criteria. It is not a qualified specification for a product. So there is no such thing as a UL 1008 device, but a product could be evaluated to and compliant with UL 1008. And there are devices that get evaluated under this criteria, and a few of those that we may be familiar with are a main ATS or automatic transfer switch in a building where we have a generator. The BCELTS we'll talk about today that works down at the zone level. And then also perhaps a transfer switch used in optional standby systems according with NEC Article 702. So what our presentation today will not address is fixtures with internal battery backup. We're not going to address egress rated lighting control panels, but we will address egress lighting control at the zone level. So we'll be dealing specifically with distributed products that are not panel based. So just to be sure that we all understand where we're at and what we're talking about, the schematic diagram is showing an emergency power source, in this case a generator, a main ATS, and then a normal/emergency panel board for our emergency power distribution. We're going to be talking about the devices that are down here at the zone level controlling a specific zone of lighting and how that interfaces with the associated normal lighting in that particular lighting zone. We will assume that an alternate life safety rated power source is utilized for egress power. Some sources that would meet that requirement are a life safety rated generator we saw in the previous diagram. And that might also be replaced with, or in lieu of the generator, one might use a life safety rated lighting inverter. And again, back to that schematic, these devices would be located at the power source for the egress lighting power. We're talking about devices down here. We're assuming there's a device at this level providing that alternate power source. So what we're not talking about is devices that have internal battery backup. So in the Article 700.2, definitions have steadily been refined since 2011 and most recently in 2020. 700.24 was updated in 2014, 2017, and most recently in 2020, and is currently identifying luminaire directly controlled criteria. 700.25 was added in 2017 and most recently updated in 2020 and identifies branch circuit emergency lighting transfer switch criteria. 700.26 was added in 2017, has not been updated in 2020, and identifies automatic load control relay criteria. So since 700.26 was not changed in 2020, we'll start out and do our deep dive here with that particular section. So ALCR is our common term we refer to these devices as. That stands for automatic load control relay. These devices are evaluated to UL 924, and the intent is that it fails to emergency lighting on in the loss of normal power. They can no longer be used to transfer the emergency light to an alternate asynchronous power source. That happened in 2017 when 700.25 was defined for BCELTS. This device holds its emergency state until the normal power is restored. So let's take a look at a schematic to understand specifically how this product works. So this dark border represents our control device. Inside of it, we have a control circuit operating a normally closed relay. for the purposes of the start of this, we're going to ignore everything on this side of the control board. We're going to focus specifically on the elements shown here in red. So what we have is the emergency hot. Again, alternate power sources generating this emergency hot. That could be a generator, it could be a lighting inverter. That power is routed through a normally closed relay and goes to the emergency light. So in this case, we say, well, gosh, what operates this relay? What operates it is this control circuit. This control circuit has some specific inputs over here that are associated with normal power and normal power lighting and lighting control. So this is the normal hot leg for our normal only lighting fixtures. We can see that this normal only light is turned on by this switch. So normal power through a switch to the normal light. That switch leg also goes to the control circuit, as does the unswitched normal hot. And the simple operation of this control circuit, which drives this relay, is this. If there is normal hot unswitched power, then this relay will track the state of this switch output. So that means if my normal lights are on, my emergency lights are on. If my normal lights are off, my emergency lights are off. But in the event we lose normal power on this black wire, this relay will fail to close because it's a normally closed relay. A very simple logic circuit and a very simple control device that allows our emergency lights to track our normal lights in a normal power condition. But in the event we lose our normal power condition, the emergency lights automatically turn on at full. Something important to note here as a designer when we're looking at loading of the lights, what power distribution system do the lights calculate to for loading purposes? Our normal light, of course, is going to be connected to our normal lighting power distribution in all cases. Notice that our emergency light is never connected to normal only power. It's only ever connected to the emergency power distribution system. So the only place that this light fixture loads is on emergency power distribution. The only place that this normal light loads is on normal power distribution. To expand our discussion a little bit, we're now going to consider some alternate inputs to this control system. So in the case that we have 0 to 10 volt dimmable lighting, we all know that a 0 to 10 volt light, when it has no connection on the 0 to 10 volt wires and it has power, will be on at full. So if we want to guarantee our performance and predictable performance for this emergency light, we need to have the 0 to 10 volt circuit controlling that emergency light go open circuit upon loss of normal power. The way this product deals with that is there's a normally open relay. In the event there's power on this black wire, that relay will close and stay closed. That allows the violet wire of the 0 to 10 volt control signal to be routed to the normal and the emergency lights. And they're then connected through this relay to the violet from the lighting control device, whatever that might be. In the event we lose power on this black wire, this relay will automatically open. And we know that that then would cause the 0 to 10 volt wires to the lights to go open circuit. And we know that as soon as this emergency light has power, it will then turn on at full. How long does that take? Well, let's kind of walk through a timeline of that. So in the event that this normal power is utility power, and we have a generator, and our emergency power distribution system is connected to utility power through an ATS, then we know that at the moment of losing utility power, we have no power here, and we would also have no power here until the generator spins up, our ATS makes a transfer, And this power distribution system is now connected to and powered from the generator. And at that point, this relay is open because we still have no voltage here. This relay is closed because we have no voltage here. As soon as the generator spins up to power, we know this light will then turn on at full. So if we were to evaluate the same condition with the alternate power source here as a lighting inverter, the only real change to this is how fast this light is on. Lighting inverters are very quick. Most of them are designed to show no power outage. So the moment we lose voltage on this black wire, we know this relay will close, we know that relay will open, and nearly instantly the emergency light would be on at full with the lighting inverter as the alternate power source. Evaluating one more of the control inputs to this, there is an auxiliary input to it that can be used for various systems. One obvious device might be a test switch to trigger this device into an emergency mode for test purposes. But since it's a contact input, we can link multiple parallel control devices here. So we could link it to fire alarm, security, or other systems, and allow them in a emergency situation to close this contact. If this contact is closed, the behavior of the device is such that this relay will be closed until this is open, regardless of the state of normal power. So this is a high level input causing our emergency light to turn on and stay on. Another way of looking at this, just a line drawing that might be used on a set of blueprints as a detail. We're showing exactly what we showed in the previous schematic here. But the difference is that we've simplified this. We're not showing neutrals, we're just showing intent here. So this is my dimming device, whether it's a panel or a wall box dimmer, we don't care. Our ALCR, and we see our emergency power is going to the ALCR. We have normal unswitched power to our dimmer device. We have normal unswitched power to the ALCR. We have a normal switch leg coming out going to our normal only lights. That normal switch leg is also going to the ALCR that's controlling the power to the emergency lights, as well as the dimming to both the normal and the emergency lights routes through this device. And if you recall from the previous slide, we had that violet wire relay in this. So yet another schematic to show this intent. Oops. I threw this slide in here just to give you an idea physically of what some of the devices associated with this category might look like. So we have a product here that's a simple 1/2-inch KO mount, could go on a 4-square box, and it looks like all the makeups associated with it would be done in that box. This is a form factor of a DIN rail. So this would mount in a DIN rail type enclosure, so conduit in, conduit out. Another 1/2-inch KO. This is a Decora style opening where the device is expecting to go in the same box as all the wires and makeups. These could potentially run into some space limitations. There's a lot of wires that go into this type of a makeup. So you add the incoming wires, the wires from the device, and all the makeups. These types of devices would probably have to be put in larger back boxes with P-rings on them. And then here we show a more robust metal type enclosure that a contractor could bring conduit entry into and out of. So let's move on to the BC ELTS, Branch Circuit Emergency Lighting Transfer Switch. This is described in Article 700.25. These are different than the ALCRs because they're evaluated to UL 1008. And what makes them different is they're a transfer device. So they transfer the lighting from one power source to another asynchronous power source. And we'll see that in the schematic diagram of this device. One of the things the code review did, while they require all transfer equipment to be evaluated to UL 1008 standards, They did relax that requirement in one sense for this product. While in a standard UL1008 ATS transfer switch, the contacts in that device need to be mechanically latched in both normal and emergency position and electrically transferred. In this particular product, due to the cost of that type of a relay type contact, and knowing that this is deployed at the branch circuit level, we have smaller lighting loads, we have way more of these devices in a building. The Code Review Committee made a concession to allow manufacturers to make a more economical product. So they did not require that that contact device be mechanically held like a main ATS. There was an update in 2020 in regard to BC ELTSs that use external fuses. More on that in some next slides. But the concept behind this product is that it reroutes the emergency lighting load, leg, and neutral to an alternate emergency power source. So let's look at what that is showing us in a schematic representation. So again, from our previous slide, we know we have a control circuit in our device. And we have a dimmer output leg and we have a dimmer output neutral. So when we say dimmer output leg, what we're really talking about is phase dimming, where we're changing the voltage to the load. So this is what we call mains dimming or phase dimming. It can be forward phase or reverse phase. That's what's different about the BC ELTS than about the ALCR. So with the BC ELTS, our dimming function is done on the power leg. So this is a phase dimmer that's outputting a varied voltage to the normal lights. And in a normal power condition, we need to connect these emergency lights to that variable output dimmer. So what we have is a contact in the device that transfers or connects the emergency lighting, both leg and neutral, to the normal dimmer output. So whether this dimmer is a wall box dimmer or in a panel, we don't care. It's a phased dim output leg coming to this device and going to the normal lights, and we're going to connect the emergency lights to that dimmer in a normal power condition. So just like our previous design, the control system sees a normal power leg and a normal neutral, and in the event there's voltage on this wire, it will connect these emergency lights to the dimmer output. In the event that we lose power on this normal power, it will then transfer these emergency lights to the unswitched emergency power leg. And if you recall, this power source is going to be our generator or lighting inverter. And as soon as those devices are on and operable, these emergency lights will be on at full. Just like our previous schematic, we also have an auxiliary contact input that allows auxiliary remote devices to close a contact and drive this device to the emergency position. So again, that could be a test switch, it could be a fire alarm, it could be some type of a security system. So this device, again, pretty simple. And let's take a look at that relaxed requirement from UL 1008. So as we mentioned in a previous slide, the code review relaxed the latching contact requirement if the circuit is not rated larger than 20 amps. So again, that fits our criteria. We're at zone level lighting control. We're at 20 amps or sub 20 amps. However, they did require that the contact device must still meet other UL 1008 requirements. So they test the load at 6,000 cycles. So that relay contact has to endure or last through 6,000 cycles at its rated load. It also has to withstand the fault current test associated with UL 1008, which is fairly strenuous. So let's look at that a little bit more. That switching device has to be designed to withstand the required short circuit current for 3 cycles. With an electrically held contact, that is quite a task because the amount of energy flowing through those contacts for that 50 milliseconds is enough to push the contacts apart. And without a mechanical latch to hold the contacts closed, they will push apart through that high current flow arc, and it could damage or destroy those contacts. It's really interesting to see this testing. When you see a fail test like this, it's quite explosive. So that's where we see arc flash and things like that occur in that testing. So the manufacturer has a choice. They can clearly mark the device for use with only specific overcurrent devices in manufacturers based on their testing. So whatever that SCCR let through current rating is, this device can stand it up to X, but there's specific breakers and equipment that could mitigate or reduce that. Well, that's pretty complex to test your product with all the gear manufacturers. So most manufacturers took that requirement and said that's not a great option. The other option was to implement an inline or series fuse that they would test and mark the product with. And the whole concept here is through that fault test, the contact, the relay in that device cannot be destroyed or fail. It has to be working after the event has subsided. So by putting an inline fuse with the device, the fuse takes the brunt of the current inrush and opens. The relay survived. The device isn't working, but this was a very clever way to get around the requirement for testing your relay contact with all the gear manufacturers. And what happened immediately is that many manufacturers didn't have the space inside their product to install these fuses, so they just shipped the product with an external fuse blocks. And if you recall from our diagram, we're dealing with branch circuit level products, so a contractor would look at these fuse blocks and a device and say, well, why do I need the fuses? I already have a 20 amp branch circuit breaker. They toss the fuses over their shoulder and the device winds up being installed without the fuses. So one of the UL use guides issued in 2018 added some language, and then they further refined that in 2020, saying that no BCELTS using external fuses can be put in service without the fuses installed, or that client or that installation would be deemed non-compliant. So some devices that you see out there in the field, and keep in mind, these are 20 amp rated devices. It is a transfer switch, so there's a lot more going on inside of this product than there was in our ALCRs. So you see that they're bigger collectively. A couple of manufacturers make them in metal enclosures, simple conduit entry exit. And another manufacturer, again, choosing to make a surface or a flush mount type product requiring external fuses. So obviously in this installation, getting these installs a little tough. So as a designer, I think it's good to be aware of what products are out there. So you may want to specify particular products that kind of, in that attempt to have predictable performance, we may want to make sure that we don't specify products requiring external fuses because of the confusion associated with them. So let's move on to directly controlled luminaires. In 2014, there was language added for directly controlled luminaires, and Article 700.24 was born to describe operation of directly controlled luminaires and how they're supposed to work. It's a very confusing category. It's not real clear even yet today in 2020. They're trying to further define this intent, but there's definitely a discussion going on at the code review committee because there is intent from certain members to move this to where directly controlled luminaires, the luminaire itself has to be listed for egress lighting purposes. As you can imagine, there's a lot of manufacturers making fixtures that are used for egress lighting. And to have all of those manufacturers submit and evaluate their fixtures for use for egress lighting is a pretty monumental undertaking. So there's pushback against that. So now the review committee is trying to further define directly controlled luminaires. So there was added definition in 2017, refined in 2020, and we're going to specifically read this today. So a directly controlled luminaire is an emergency luminaire that has a control input for an integral dimming or switching function. That signal drives the luminaire to the required illumination level upon loss of normal power. This is pretty important right here because this basically is saying the fixture doesn't have to go to full, it only has to go to the required illumination level to meet the egress requirements. So this is where the code review allowed partially driven fixtures for egress lighting use. You don't have to have the fixture come on at full. And there are systems out there that partially drive the luminaire in an emergency condition. And in our agenda to have predictable performance, that requires a pretty solid spec and maybe assurance that the light fixture evaluated, the control system evaluated are actually what's supplied to the project to ensure that performance in a partial illuminate or a partial light output condition. So the NEC introduces or has a handbook where they introduce commentary to help us understand what they're talking about and avoid misusing or misapplying their language. Their language is not always clear and concise. And I think the handbook is very useful in trying to tunnel into specifics of what are we really dealing with here? What are they trying to say? So on 700.24 for controllable luminaires, there's some language in there in this handbook commentary that helps us understand the different types of controllable luminaires. So they specifically go to the effort right here and describing this as an ALCR bypass device and opening of the control circuit. Well, we've already looked at that under 700.26, so we know that product exists. We know it works for 0 to 10 volt. The question you might ask is, wow, will it work for other type of fixtures that have a control signal input? Other types rely on an active signal from an emergency control system to set the required illumination level. So that would be a system that has an emergency signal going to the lights. So some additional narrative associated with that, I think it's very interesting how the code review keeps coming back to predictable operation. That's why this is highlighted. And that's really what we want to focus on here as we look through these directly controlled luminaires. In what condition as a specifier can you specify a system or a device to control a directly controlled luminaire where you have predictable operation? So what they did was break the directly controlled luminaires down into what are basically 3 categories. And we're going to look at each one of those individually. So the first is luminaires where the absence of a control command causes the luminaire to illuminate at full. And we try to refer to this as loss of signal because the rest is a lot to say. So we're going to go back to a schematic that we looked at previously and evaluate it and say, well, loss of signal. How can we guarantee loss of signal from the control system? Well, gosh, how about if we open the control signal wire? That's what we're doing in the ALCR. We've already looked at this. We know this works for 0 to 10 volt. The question might be, hey, is it going to work for other types of lighting control? So 1 to 10 volt is what we refer to as 0 to 10 volt. From an electronic perspective, that's actually a 1 to 10 volt signal. You may or may not be familiar with DALI, which is a 2-wire digital signal. So to go back to this, if one of those DALI wires was routed through this contact and opened, the fixture would no longer have a DALI data signal in a loss of normal power situation. So the behavior of a DALI driver is such that if there is no DALI signal, it turns on at full, just like our 0 to 10 volt drivers do. So I believe we could say that this solution, the ALCR solution, would work for a DALI type device. Another digital signal that we might use in the field for emergency luminaire is DMX. And so the question is, if one of our data wires for the DMX was routed through this contact and it goes open, we know that our lighting control or our lighting fixture would lose the DMX data signal upon loss of normal power. And then we say, well, gosh, what's that driver's behavior on loss of normal power? And the answer is it depends, because there are DMX drivers that upon loss of the DMX data signal go on at full. There are DMX drivers that upon loss of the DMX data signal turn off because there's no drive signal. There are DMX drivers that upon loss of the DMX data signal do nothing. They hold last look indefinitely in some cases. So we kind of have 3 different conditions there. So back to that predictable performance statement, we can't really guarantee predictable performance in this condition using DMX with the ALCR because we don't have intimate knowledge of what the DMX driver's behavior is upon loss of data signal. So one might think, well, gosh, then I'm going to specify a DMX driver that goes to full on loss of data. Be very careful about that because the behavior of that DMX driver is such that it has to have a loss of DMX data for a certain time frame before it will go on at full. And I've been burned on projects where the DMX data signal has to be lost, the fixture has to repower with no DMX data signal before it'll come on at full. Other fixtures may wait 10 seconds, 15 seconds, or 20 seconds. After 20 seconds of no DMX data, the fixture will automatically illuminate at full. So there's all those conditions. So based on our predictable performance, my comment is this may not be a good solution with an ALCR type device. Another type of luminaire is a luminaire where an external input causes the fixture to ignore the data input signal and illuminate. We refer to these as external input type fixtures. So looking at a schematic of that, this is what it might look like. We have unswitched emergency power, or perhaps this is switched through a qualifying device like an ALCR to the emergency lights. We have a control signal to the emergency lights. We have an unswitched normal power wire going to the lights. So this is basically sensing normal voltage. And the driver inside the fixture has all the smarts that says, hey, if I don't have voltage here, as soon as I have voltage here, I'm on it full and I'm ignoring the control signal. It's like, wow, that's very, very simple. That would alleviate a lot of the pain with how do I lose the control signal? What's the behavior of my driver on loss of control signal? A lot less evaluation here because this product is basically fixture specific, control agnostic. We don't care if this control signal is 0 to 10. We don't care if it's DMX. The whole function is based on this input. If this input has voltage, we'll listen to this. If it doesn't, we're on it full as soon as we have voltage here. Really simple system. So one might ask, wow, where do I get a fixture like that? And done a little research. There are fixtures out there today. There are manufacturers who are specifically focused on making fixtures that perform like this. So this is a super simplified system. And the beauty of it is it's control signal agnostic. So it takes a lot of the stress off the designer. And we know what our predictable performance is going to be here because we don't care about the control signal. Voltage is gone here, bam, we're on it full. So a really simple system. And the beauty of that external input system is that it's data signal agnostic. It's a fixture level feature. So the fixture is the product that gets evaluated to UL 924 standards and so listed as a directly controlled luminaire that meets the requirements of external input. Another type of luminaire is a luminaire where an override command is received on the control input. So what's that look like? What's that really mean? So we're going to go back to the good old schematic diagram and say, well, if my emergency light has a device in the switch power circuit that's so rated, and my control signal device is rated to UL 924 such that upon loss of normal power, it's going to send out a signal that says, hey, all lights at full. Now we're compliant. And I guess we don't really care what this control signal is as long as we have a device that will send all lights to full down that control wire. So what are the complications associated with this? Well, the first complication and the most obvious is, where do I get one of these? We know we have these devices, but where do I get a UL 924 rated control signal from? To discuss that, I'm going to go to a slide of a very specific use case. Our use case is DMX data. And what we're looking at is egress lights. So basically what we're looking at here was the same schematic we just looked at, with the exception that our control signal infrastructure changes. So there are devices made today that are called DMX emergency bypass controllers, and their behavior is such that upon loss of this normal power, this device sends a contact closure to this DEBC. The function of the DEBC is to stop listening to the DMX signal from the normal control system and use an internally generated DMX signal that sends data down the wire that says all lights at full. Now, this is a proven and robust system, and it's been deployed for many, many years. It works. So there are products out there that do this. There's multiple manufacturers of them, so you're not stuck with a particular brand. But one of the things to be careful about in this condition is that the type of DMX light fixture you use cannot be the type of device that auto addresses. So there's light fixtures out there today that will grab their addresses off the DMX data stream, reproduce that signal, and send it on. And each fixture grabs the first group of channels it needs, reproduces the signal, and sends it on. So this is active data repeating in each one of these fixtures. So in that condition, if the driver in this fixture fails, this fixture will illuminate in an emergency condition. This one won't, because this driver failed and cannot repeat the data signal to this fixture. So if you're going to deploy this type of a system, the one thing you do need to make sure of is that you don't have an auto addressing type DMX fixture deployed as your emergency fixture. So back to that condition of predictable performance. The performance here is predictable as long as you don't deploy a type of fixture that repeats that data signal actively. In the event that we're using an override command on the control input like we just discussed, we know that we have a DMX solution out there, And we know that the DMX source needs to be evaluated to and compliant with 700.24. Many people ask me about PoE Ethernet. What's out there for that? So if the Ethernet switch was evaluated to and compliant with 700.24, then I would think there could be PoE Ethernet fixtures used for egress lighting purposes. I personally am not aware of any PoE Ethernet switches that meet 700.24 today. If that type of a product is continuing to grow and be used, I'm sure there's action underway to determine how to get that switch evaluated and listed. Are there other digital data signals or analog data signals that could go to fixtures where that data source could be evaluated to and compliant with 700.24? Most certainly. Are there any out there today? I'm not aware of other proprietary data signals that have a compliant signal generator to be used as emergency egress lighting. So if we go back to the three approaches for directly controlled luminaires, we have a loss of signal, which is compatible with our current 0 to 10 volt or 1 to 10 volt world. We know that would also work for a DALI product. It could work for DMX dependent upon the driver, but back to the predictable behavior, we're kind of relying upon the driver and the fixture, and sometimes we might lose control of specification on the fixture and or what's supplied. So we may not be able to predict the behavior of the DMX driver. So this would be a solution you want to give some deeper thought to, and definitely a deeper dive and technical understanding of the equipment. External input, this seems pretty simple. It's fixture based, the fixture qualifies, you're off to the races. This is a fairly easy approach for using a data-driven luminaire. An override command on the control input. We saw a case, a schematic, where we know there's product out there that allows us to do that with a DMX data signal. Ethernet, again, a special case where we're not sure if there's product that's so rated or listed. And then, of course, we might want to add a category here for other type of proprietary digital control signals that might also meet that criteria. So to make a summary and kind of a wrap up here on our presentation today, we have talked about life safety systems. So encouraging designers not to make design decisions based on economics or economy and or commercial packaging concerns, to stick to your guns with this equipment because it is a life safety issue. And unfortunately, there are applications that are just going to require a more extensive approach and deep dive. The designer will have to know their hardware, their code, and may even have to do a test case to ensure performance, to avoid any kind of misapplication for the egress lighting control system design. And we always want to know that our core competency is always measured by predictable performance. Do we have a system where if we lose control of the light fixture specification and light fixtures are supplied that we didn't qualify, or a control system is supplied that wasn't qualified in the spec, can we still ensure predictable performance in a life safety situation? So at this point in time, I'd like to thank everyone for your attention and open the presentation to any questions that might have come in during our discussion. Carl, did you get any questions?
You know, Shane, I think you must have anticipated everybody's questions and hit them ahead of time, because we've got nothing coming in on the Q&A.
All right.
Oh, just kidding. We do have one coming in on the chat. I'm going to read it off here, Shane, for you to answer out loud. LED tape light keeps getting more prevalent. I'm seeing tape light even used for emergency lighting. I'm concerned about its use. Could you speak to that, please?
Well, the tape light product itself isn't going to dictate the success or lack thereof of its use for an egress application. So we really have to start evaluating its associated driver or power supply. And can that driver or power supply be implemented into our lighting control strategy and be code compliant? So LED tape as an emergency lighting source, I guess it's a designer's personal choice. We know that there's a lot of downward price pressure on tape that is driven to very low levels of pricing. And how robust is that product and what kind of warranty can you get on that tape, or what would its anticipated lifespan be? Would be where I'd get a little concerned about using tape. But there are also really robust commercial grade tape products out there. So if you're in a situation where you have to use a tape type product as an egress source, definitely give some attention to the quality level. Is it a commercial duty rated product? What type of warranty are you naturally getting on that product? And how assured can you be that the tape and its associated power supply are robust commercial duty products that the owner isn't going to have to replace in a couple of years?
Thank you, Shane.
You're welcome.
So if there are any more specific questions, yeah, I agree with some of our attendees that this is a lot of good information, emphasis on a lot. And I'm sure many of you are like me and appreciate technicalities and appreciate semantics. And so understanding the difference between an ALCR and a BCELTS, and how understanding that just saying UL 924 device is only part of the picture.
Please don't do that.
Yep.
And rest assured, we'll be back in 3 years because there'll be new updates. We do anticipate more action, particularly in the directly controlled luminary categories. I think ALCR and BCELTS are pretty stable. We don't anticipate a lot of changes there. The only thing we may see in the BCELTS category is some additional action taken on the external fuses. My understanding is the code review committee is moving towards disallowing products that require external fuses, that the fuses will have to become an internal component of that chassis.
Very good.
I can't believe it. Nobody asks about wireless lighting controls for egress. All right.
All right.
Excellent.
We do have some more questions coming in now.
Okay.
All right. From Allison, if the fuses do fail, do you have to replace the whole relay?
No, the purpose of the fuses is to ensure that the fuses fail prior to the relay contacts failing. So that's the purpose of and why those fuses are there. You would only replace the fuses.
Makes it easy. We have one from Jeffrey. We'll put you on your toes, Shane.
Okay.
Can you speak to the 2018 IBC emergency egress site lighting requirements and the interfaces with site lighting controls, especially in regard to 24-volt site lighting and NEC requirements for alternates at the branch level?
Wow, that's a loaded can of worms. I think we should probably take that offline.
Yep.
I guess I'm not quite sure what our control device is going to be there if we're using a field-mounted photocell on the luminaire, if we're using a field-mounted photocell control combination on the fixture itself. But the code has been acceptable to automated lighting control devices such as external photocells. We're not disabling that device if that device is sourced, its power sourced from emergency power. In an emergency condition, that device would be anticipated to continue operation as intended during a normal power condition. So if we have an active photocell relay mounted on a, say, a pole type fixture on a NEMA socket, that device should continue to operate as designed. So if there is a condition where we're in a low light level, it'll automatically come on. If we're in a condition where the light level is very high, we lose power during the day. There's no reason for that product to come on during the day. There's a lot of different potential ways we could go with that discussion. So that might be, perhaps Jeffrey would like to just reach out via email. I've got my email information here, and he could also call and we could discuss the particular situation or application in detail that he's looking at.
That sounds good. Allison, thank you for taking the tee up. Shane, what are your thoughts on wireless control systems for emergency lighting?
Please don't. And I want to explain that. I don't want to just blurt that out and walk away from it. There are wireless lighting control systems produced today that have been evaluated to and passed use for egress lighting control. The thing to understand about that is there's a very specific use case where that's functional, and it kind of goes back to that whole concept of predictable performance. The way wireless lighting controls tend to work when they're egress listed is that the device relies on it. So let's say I've got a relay controlling a zone of lighting, or I've got an embedded device in a fixture to make it a wireless device. That lighting control device is requiring on a loss of power and a return of power with no wireless signal to know it's in an emergency situation and turn on. That works pretty good with an emergency generator because we have a utility power outage. We have a time frame during which the generator has to spin up, the ATS has to transfer, and then we reestablish power on our emergency power distribution system. But in the event that we have a lighting inverter, that wireless lighting control device did not experience a loss of power, so it did not reboot. It stayed online, and the wireless signal goes away, and it comes down to how's that product designed to perform in a loss of wireless signal communication when there's not been a power outage. And in most conditions, that device will be programmed to hold last state. Well, in the event that we lost power when the lights were off, its hold last state is lights off. In the event that device was on at 30% because someone dimmed the lights, but we need it on at full to meet our egress requirements, that device will hold last state or 30%, and we don't meet our egress requirements. So my understanding is that in 2023 review, or perhaps prior, that the wireless lighting control systems requiring a power outage to determine it is in an emergency condition will be disallowed. That's what I'm hearing, so I guess you could qualify that somewhat as gossip. But when we look at the logistics behind the situation and the code review's attention towards guaranteed predictable performance, one might understand why that technique is falling upon disfavor.
Yes, so proceed with caution if you have a wireless control system and are doing your emergency lighting from it. Make sure you definitely understand the logic of that specific control system so we're not leaving anyone in the dark.
Please do. Yes.
So we have another question collectively from A Design. Are we to understand that the emergency light and regular light can be on the same control zone?
From In the situation where we're using an ALCR or we're using a BCELTS, the answer is yes.
Easy.
Can you put them on a separate control zone? The answer is yes. And when I say them, I mean the emergency lights. Could you design it such that they're on their own lighting control zone? You may need to use them as night lights. In that case, you would design the emergency lights to be on their own zone and not controlled as a subordinate of a normal lighting control zone. So you can do it either way. Of course, the most economical way is going to be having them as a subordinate set to a normal lighting control zone.
Excellent. Well, that catches us up on all of the written questions.
Great questions.
Absolutely. I'll give you a few more seconds. If anyone else has any more questions, comments, I'll reiterate that we will make this presentation available after here. We'll send it out in a link so that everyone has access to this again.